Hello, this is my Physics Lab 3, Black Hole and Orbits. For this lab, the purpose is to create various computational models that demonstrate Newton's law of gravitation. We will explore how multiple forces of gravity affect an object and its momentum. In Part 1, the goal is to estimate the mass of a black hole based on its interaction with a star of known mass. In Part 2, the goal is to determine the initial velocity of a spaceship that is required for it to not crash into anything while it is being affected by the gravitational forces of a planet and moon. The fundamental principles covered in this lab include Newton's second law, which state that the net force is equal to the change in momentum over the change in time, parallel net forces, perpendicular net forces, the law of universal gravitation, velocity update formula, and the position update formula. The system for this lab is the black hole, and the surrounding is the star. The assumptions made for Part 1 is that the total force is the magnitude of the single force of the black hole acting on the star, and for Part 2, the only forces are the gravitational forces between the planet, the moon, and the spaceship. When setting the initial conditions for Part 1, we edited the lines of code for the mass of the star and the time interval between the imported data points as seen below. When editing the code for the iterations for Part 1, we set the initial and final momentum vectors, the star's change in velocity and change in momentum, dp over dt, fnet, parallel components of db dt, parallel component of fnet, and the perpendicular components of db dt and fnet. Here are the results from the code from Part 1. Aligning with the law of universal gravitation equation, which relates the force of gravity directly to the inverse square of the center-to-center distance, we can see that as the star moves closer to the black hole, the gravitational force increases. Also aligning with the fundamental principles of fnet, parallel, and perpendicular forces, we can see that the light blue arrow, which represents fnet perpendicular, aligns with the n-hat axis, which points towards the center of the kissing circle, and the purple arrow, which represents fnet parallel, aligns with the p-hat axis, which points parallel or anti-parallel to the motion of the object accordingly. From this model, we determine the mass of the black hole to be 3.99 times 10 to the 64th kilograms. For Part 2, we set the initial conditions for the ship speed in the x direction and the ship speed in the y direction. When editing the code for Part 2, we found the equations for the force of the planet on the moon, the force of the ship on the moon, the net force on the moon, the force of the planet on the ship, the force of the moon on the ship, the net force on the ship, the moon's velocity and position, and the ship's velocity and position. Here are the results from the code of Part 2. Based on these results, we can see that the ship's trajectory, which is shown by the purple line, is influenced by the planet, shown in dark blue, and the moon, shown by the light blue line. From this, we know that the initial velocity required for the spaceship so that it does not crash is 20,000 meters per second for the x direction, and for the y direction, it is the speed of the moon times 1.5 meters per second. Based on the perfect circle shown with the light blue line, we can observe that the moon moves in constant circular motion around the planet. Based on these results, since the change in momentum matches the direction and magnitude of the net force, we can conclude that both models support the fundamental principles of Newton's second law. We can also see in both parts that the gravitational force explains the curving motion of the object. For Part 2, we can see that the moon's orbit align with a simple two-body diagram. However, since the line representing the spaceship's orbit is not a perfect figure 8, we can see how sensitive gravitational interactions in a three-body system are to their initial conditions. Possible sources of error could have included ignoring other forces that could have affected the orbit of the objects, rounding errors when approximating the star's mass, and choosing a smaller delta t for Part 2 could have increased accuracy. What does this mean? When comparing the parallel and perpendicular components of net force versus momentum, we can see that although they are the same magnitudes, they are calculated differently. For the net force components, you simply add up all the forces acting on the system. However, for the rate of change in momentum, you must observe the change in motion of the system and analyze its velocity, mass, and delta t. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? For this model, we would need to include calculations for the gravitational forces of all objects included in the system and find the net force acting on each object. Considering that the black hole is the greatest mass, the gravitational interactions that are influenced by the black hole will be the most dominant.